Hello everyone. In this talk, I will present an article called Decisiveness of Stochastic Systems and its Application to Hybrid Models, which has been accepted to Gandalf 2020. This article is a joint work with Patricia Bouyer, who works at Université Paris-Saclay in France, and with Thomas Brihaye, Mickael, Randour, and Cédric Rivière, who work in Mons in Belgium. First of all, a brief outline of the talk. So this talk will be focused on the verification of models that combine two features. First of all, stochastic aspects, which you can, for instance, find in Markov chains. And second, hybrid aspects, which means that the systems will exhibit both discrete and continuous behavior. A typical example of a hybrid system is a plane, because it is subject to continuous factors such as heat, speed, and pressure, but it is also subject to discrete events, such as the ones by the computer that governs the plane. And so what we'll study will be called stochastic hybrid systems. And we will be focused on the reachability problems about these stochastic hybrid systems. So as we are in a stochastic context, reachability problems could be, for instance, is some set of states reached with probability 1? Or can we compute or at least approximate the probability of reaching a set? And these problems are very much undecidable even for hybrid systems without stochasticity. So what we want to do in this work is to, in a way, identify a decidability frontier for reachability problems in stochastic hybrid systems. That is, we want to find a class of stochastic hybrid systems that is as large as possible and for which reachability problems are decidable. And the method that we are going to follow is an approach that has been successful for infinite Markov chains and which was presented in an article from 2007 called Decisive Markov chains. And so the first part of my presentation will be to recall this method. And then we will see how we can actually apply these ideas to the more complicated systems, which are stochastic hybrid systems. So let's start with Markov chains. So we will consider a countable Markov chain. So this example is even a finite Markov chain. We will always define some target set of states. In this case, it will be lowercase a, and an initial state. In our example, it's C. And what we actually want to do is to compute or at least approximate the probability of reaching B from an initial state. So the notation diamond B means all the infinite runs that go through a state in B at some point. And our first definition will be given B a set of target states, B tilde will be the set of states that reached B with 0 probability. So in our example, if our target state is lowercase a, then lowercase a tilde will be the set of states that consists only of the state lowercase d, because from D there is a 0 probability to reach A, whereas from B and from C there is a positive probability to reach A. So I'm sure you know plenty of ways to compute such a probability, but I'm now going to present a method that can actually later be extended to infinite Markov chains and even to uncountable stochastic systems such as stochastic hybrid systems. So if we want to compute the probability of reaching B, what we can do is first of all to define two sequences, so which are called P and yes for some natural number n and P and no. So P and yes will be the probability to reach B in at most n steps. And so that's very easy to compute for a Markov chain because there are finitely many paths of length at most n. And similarly, P and no will be the probability to reach B tilde in at most n steps. And so we know that when we reach B tilde, the probability to reach B is 0. And so the probability to reach B is actually always lies for all natural numbers n between P and yes and 1 minus P and no. Because when we reach B in less than n steps, we know that we've reached B. And if we reach B tilde in less than n steps, then we know that we won't be able to reach B. And so this algorithm, or this procedure at least, takes as an input some positive epsilon And it stops whenever the gap between 1 minus p and no and p and yes is at most epsilon. And so this means that we have actually been able to approximate the probability of reaching B epsilon closely. So we can apply it to our previous example with the Markov chain with 4 states. So our target state is A, and we know that A tilde is D. So if we start from C, in 0 step, we know that we haven't reached neither A nor D. So P0 yes will be 0, and P0 no will be 0. In 1 step, we know that we can reach D with probability 1/2. So P1 no will be 1/2. And we keep unfolding the Markov chain. So in 2 steps, we can reach A with probability 1/4. So P2 yes will be 1/4, while P2 no will still be 1/2. And so on. So you can notice that Pn yes and Pn no are always non-decreasing sequences. And in just 3 steps, we can see that the probability to reach A from C lies between 1/4 and 3/8. So that's very good, and it works quite well. But we can wonder whether such an algorithm always terminates. And unfortunately, it does not always terminate. So here is an example of an infinite Markov chain for which such a procedure does not terminate. And this is actually a random walk on the natural numbers. And so it's a diverging random walk because in each state, you have probability 2/3 to go right and only probability 1/3 to go left, except in S0, where you are sure that you go to S1 at the next step. So our problem will be stated as follows. So our initial state will be S1, and we wonder what's the probability to reach S0 from S1. So our target set of states, B, will be the S0. The first thing you can notice is that in this case, B tilde is the empty set, because no matter in which state you are, you always have a non-zero probability to reach S0. So what can we say about P and yes and P and no? So for any n, P and yes, as we've seen, is always less than or equal to the probability to reach B. And we can actually compute via other means, because this is a very well-known example, that this probability is 1/2. So P and yes will always be less than or equal to 1/2. And as B tilde is the empty set, P and no will always be 0 for all n. And so what you can notice is that the gap between 1 minus P and no and P and yes will always stay bigger than 1/2. And that's an issue, because if you had taken an epsilon that is too small at the beginning of your algorithm, then this algorithm won't terminate. So now to remedy this problem, in the article Decisive Markov Chains in 2007, a definition was introduced which tries to characterize the Markov chains for which this procedure actually terminates. So let us take M a Markov chain and B a set of target states. And we will define the decisiveness notion. So a Markov chain will be decisive with respect to the set of target states if for any initial state, the probability to reach B or B tilde is 1. And the main theorem is that if the Markov chain is indeed decisive with respect to B, then the approximation procedure is correct and terminates for any positive epsilon. So our previous example of the diverging random walk was not decisive with respect to S0, because we could compute that the probability to reach B or B tilde from S1 was actually 1/2 and not 1. And so what I've presented here is the algorithm to approximate the probability of reaching a set of states. But decisiveness also allows for a procedure to verify almost true reachability, that is reachability with probability 1. And so the idea is that decisiveness actually tries to avoid weird behavior where some set of states can always be reached, but not with probability 1. And the first contribution in our work is a decisiveness criterion, that is a way to check that some stochastic system, or some class of stochastic systems, is decisive with respect to some set of states. And so I will present here this criterion. So in this case, we won't only consider Markov chains, we will consider more general stochastic transition systems. That is, you can think of Markov chains, but they can also have uncountably many states, not only countably many states, or an arbitrary number of states. So we will assume that this stochastic transition system has an attractor, that is a set of states that is reached with probability 1 from any state of the stochastic transition system. So as usual, we will consider a set of target states, B. And the criterion goes as follows. So the attractor A can always be split into two possibly empty parts. So there will be some states that are in B tilde, here the red zone. That is, from these states, you can only reach B with a 0 probability. And what we require of the other states of the attractor is that they can reach B with a probability that is lower bounded by some positive probability P. So if for all states in the blue zone, you can reach B with a probability that is at least P for some uniform bound P, then it means that your stochastic transition system will be decisive with respect to B. And so this criterion actually generalizes known decisiveness criteria from the literature. So from two articles that considered the decisiveness notion first for Markov chains, and then for more general stochastic transition systems. And so we can use it to show the decisiveness of finite Markov chains, which was proved in the first article in 2007. Also the decisiveness, for instance, of probabilistic vector addition systems with states which are decisive with respect to upward closed sets. We can also show the decisiveness of one clock stochastic timed automata with respect to any set of states. And the part that we are going to be interested in the second part of the talk is that we can also use it to show the decisiveness of some class of stochastic hybrid systems. And that's what we are going to study now. As I've said in the introduction, hybrid systems are systems that combine both continuous and discrete transitions. So you can define them as follows. So it will be the given of a finite graph. The states of the graph will be called locations. So here we have 3 locations. And a certain number n of continuous variables. In this case, we have 2 variables, x and y. So the states of our system will be the given of one discrete location and values of the continuous variables. So it will be in L, the location, times r to the power of n, where n is the number of continuous variables. So that means that the state space of our systems is uncountable. Then in each discrete location, the continuous variables can evolve over time. So for each discrete location, there will be a function that maps to some values for the continuous variables and some positive value which represents time, the new value for the continuous variables after the time has elapsed. So this will be called continuous dynamics, which can be different in each discrete location. We can also restrict which discrete transitions can be taken by restricting which values of the continuous variables are allowed to take the transition. So for instance, in this case, we could only take the rightwards edge if the value of y before taking the edge is greater than or equal to 1. We can only take the leftwards edge if the value of y is less than or equal to -1. So this will be called a guard on each discrete transition. And after taking a transition, the values of the continuous variables can be reset into some set of states, into some set of values. So for instance, if we take the rightwards edge, the values for x and y will have to be reset to some value in the square -1, And if we take the leftwards edge, the values of x and y have to be reset to 0. So this is called a reset mechanism. How does a transition in such a system work? So I recall that the states of our system will be the given of a discrete location and the values of the continuous variables. And a transition will combine both a continuous evolution and the discrete transition. So let us assume that we have some state here, which is in discrete location L1, for which x equals 2 and y equals 0. So a transition will first consist of continuous evolution. So we will stay in state L1 for some time tau, so some positive time tau, during which the value of the continuous variables will evolve. Then we check which guards are allowed. So in this case, the value of y is greater than or equal to 1. So only one edge, only one discrete transition is allowed. So we take it. And then we have to reset the values of x and y to some value in the square minus 1, 1. So for instance, it could be 1/2, 1/2. So the new state after the transition will be discrete state L2, x equals 1/2 and y equals 1/2. So in regular hybrid systems, everything happens non-deterministically. That is, all the possible transitions are considered. But in our case, what we want to do is a stochastic system. So what we'll do is that we replace the non-determinism of hybrid systems with probability distributions. So we will have a continuous probability distribution on the waiting time from any given state. Then there will be a discrete transition on the edge choice for all the edges for which guard is satisfied. And then we will have a discrete or a continuous probability distribution for the choice for reset value, depending on what possible reset values are allowed. And so this gives us a model of stochastic hybrid systems, which I would refer to as SHS in the slides. Reachability problems are famously undecidable for hybrid systems, and it's also the case for stochastic hybrid systems. So more precisely, if you have a stochastic hybrid system H, an initial distribution on the states, and a target set B, then the following reachability problems are undecidable. So it's undecidable to verify whether we reach B from the initial distribution mu with probability 1. It's also undecidable to verify whether we almost surely avoid B, that is, we reach B with probability 0, always from an initial distribution mu. And it's also undecidable to check whether a value is epsilon close to the probability to reach B for all positive epsilon. So the way we've done that is by extending a well-known proof of undecidability of non-deterministic hybrid systems. And we were able to obtain also the undecidability of the approximation, which did not make sense in a non-deterministic context. And so our goal, as I've said in the introduction, is to find a setting or a class of stochastic hybrid systems in which reachability is decidable. So a very common technique to show decidability of the reachability problems for hybrid systems is to try to find some finite abstraction of the state space. So in a non-deterministic context, this is what is sometimes called the time abstract bisimulation. So that is a finite partition of the state space that preserves the properties to be checked. So for instance, all the states from the blue region will be bisimilar if they can all reach the same regions of the state space. So in this case, we put all the states from this region into the same state, and then we have a new system which is smaller than the original system, which is called then a time abstract bisimulation. So for stochastic systems, it works pretty much the same. So we will say that two states are in the same part of the partition if they can all reach the same regions with a positive probability. So we don't only look at transitions, but we look at which transitions have a positive probability to happen. So in this case, all the states from the blue region can reach the red region with a positive probability. And in this case, we talk about a finite abstraction. So this is sufficient to verify positive probabilities of reachability, but it is not sufficient to verify almost reachability. That is, it's possible that in the abstraction, some region is almost surely reached, which is not almost surely reached in our original system and reciprocally. So what we want to do is to add an extra requirement on all finite abstractions, which is the following. So we'll say that the abstraction is sound whenever if some region of the abstraction is reached with probability 1, then its inverse image must also be reached with probability 1 in the original system. So this is not always the case when we have an abstraction, and so we would like to have this property so that we can check almost your reachability on the abstraction to obtain it for the original system. So multiple classes of hybrid systems and stochastic hybrid systems have been shown to have such a finite abstraction. So in the non-deterministic case, there's a very well-known case of the timed automata, which are a subclass of hybrid systems with very simple dynamics and resets. And in this case, the finite abstraction is called region graph. There is also the slightly more general case of initialized rectangular hybrid systems, which is slightly more permissive towards the dynamics, but which has some requirements for the possible resets. And we also have a minimal hybrid systems, which are extremely permissive towards the dynamics because they allow all dynamics that are definable in some logical structure. But all the variables have to be reset at every discrete transition to have a decidability. So you can see that in these examples, there is a trade-off between being permissive towards the dynamics and being permissive towards the resets. So in the stochastic case, two classes of stochastic hybrid systems have been shown to admit a finite and sound abstraction. So one example are the single clock stochastic timed automata, which are stochastic timed automata with just one continuous variable. And the way it is done, so it's first by showing that they indeed admit a finite abstraction, but then to obtain soundness, it is sufficient to have the finite abstraction plus the decisiveness of the original systems. So if you have finite abstraction and that you show that the original systems are decisive, it means that the finite abstraction is actually sound. And so you can use it to verify almost your reachability properties. So that's what we wanted to do. And we wanted to have an example that is slightly more permissive towards continuous dynamics. So we took some ideas from a minimal hybrid systems about what to do with the resets. And we decided to look at stochastic hybrid systems that have strong reset. So a strong reset is a reset that does not depend on the value of the variables. So here is an example of what is not a strong reset. So in this case, when the value of x is, for instance, -2 before taking a transition, after the transition, x is reset stochastically inside the interval x minus 1, x plus 1. So that is, if x was -2, it will be reset stochastically with a uniform distribution inside the interval -3, -1. And so this is not a strong reset because it depends on the value of x before taking a transition. Now we can just slightly change it to obtain a strong reset. So in this example, no matter what the value of x was, it will be reset stochastically inside the interval -1, 1. And so if this is a strong reset because it does not depend on the value of the variables before taking a transition. And we were able to prove two very convenient results of stochastic hybrid systems with sufficiently many strong resets. So the exact condition is that also require stochastic hybrid systems to have at least one strong reset per cycle of the discrete graph. And when that's the case, then the systems admit a finite abstraction, which is very close to the proof for the non-deterministic hybrid systems. But in this case, very importantly, we were able to show that stochastic hybrid systems with sufficiently many strong resets are actually decisive with respect to any set of states. And we were able to show that thanks to our decisiveness criterion that I've presented in the first part of my talk. And thus, such stochastic hybrid systems admit a sound and finite abstraction. And so reachability is decidable when the abstraction is computable, because then you can just verify the reachability properties on the abstraction. As a conclusion, I recall a few classes that have been shown to admit a finite abstraction that you can use to check reachability properties for hybrid systems. And thanks to our work, we can now add a new line to this list, which is the class of strongly reset stochastic hybrid systems. So reachability is decidable under some effectiveness assumptions, which I won't have time to discuss. And we were able to show the soundness of the abstraction thanks to the decisiveness theory and thanks to all new criterion to check the decisiveness of stochastic systems. So this ends my presentation. Thank you very much for your attention.